Okay, good morning, good afternoon, or good evening, wherever you are. My name is Daniel. I will be presenting a very general overview of some of the research that has been conducted at Monash. And one of the things that we are focusing on is really on creating a sustainable future where we focus on green materials. Okay, so some of this may be very generic, but some of this may be a bit more specific. But let's walk through. I'm a concrete person, so a lot of the things that I will be covering is mainly in the area of concrete. So I'll be talking through some of the problems, drivers, and strategies, to create a sustainable future. And then I will move on to some areas of green concrete applications. Talk about geopolymers. Is that the answer? Some of you may know what geopolymers are, but if not, this will give you an overview of what they are. Talk about the current state and the art of developments, and also perhaps looking through a case study that is moved on from just a laboratory setting and more towards an industry adoption. Okay, and looking at the uptake barriers as well. So that's just the general overview of my presentation for today. Now, so let's just quickly walk through and see what is wrong with the current cement-based concrete. Okay, so this is obviously something that we're very familiar with. Concrete has been used for the last, couple hundred years, and there are many examples of concrete structures out there because this is probably the most widely used material. But many of us will probably know that there is a life, or rather a durability problem with concrete. Generally, it starts to deteriorate after about 20 years, and we have to then do some retrospective applications, or rather some treatment to ensure that it goes on further. Now, the other problem that we have with that is, of course, it also is one of the highest, most energy intensive material that is being used. And of course, the main problem is, of course, global warming, and it's also one of the main drivers of climate change. So if we are not just looking at polluting the polluting vehicles on the highways, if we turn our eyes to cement manufacturing processes, this is also a big thing here because they do contribute up to about 8% of the global CO2 emissions. And of course, we all know this. After water, concrete is probably the most widely used substance on Earth. And then one of the worst culprits out there is all the developing nations because, of our rapid urbanization. Okay, so there's definitely some things that we can address by looking at other options aside from the cement-based concrete. Now, of course, as I mentioned to you, demand keeps increasing. We are still expanding. So definitely there are some fundamental changes that we need to look into to see whether we can improve the situation in the overall. I've mentioned some of these things already. Cement, as you may know, is the main ingredient for concrete. And even before concrete comes to, is produced, the cement itself does have a fair bit of greenhouse gases that's emitted into the atmosphere. So a lot of strategies are to look at the cement, or rather replacing the cement. And I'll talk a little bit about that. But of course, there are other ways and solutions to doing this. So some of the things that you may have heard before is this whole perception of green concrete. And we'll talk a little bit about what green concrete actually means or is, okay? So yeah, what is green concrete? This is the definition. It is an eco-friendly material. Sometimes can be deemed as utilization of some waste material, okay? So at least one component of it is a waste material, whether it's in the production process or at the later stages. But of course, there are many options if you look at that particular interpretation of what green concrete is. So you can look at replacing the aggregates within it. You can look at, as I mentioned to you, looking at the cement, which is the main culprit itself. Of course, looking at other options, and the main target here is to look at something that we can, promote a life cycle sustainability in the long run. Okay, so that's just the very generic definition of what green concrete is. So some of the strategies that are out there to produce this is, of course, like I said, mainly we focus on reduction of CO2, looking for cleaner technologies. Even if you look at cement itself, can we then look at more efficient ways to produce it? A lot of it involves, policymakers. We here, based in Malaysia, we are actually one of the largest growing nations, or rather in terms of urbanization in the region. So we probably contribute quite a fair bit of percentage. I have got some stats here. In 2019, probably an old stat, but it's still relevant. We actually are one of the top emitters, Malaysia that is, in the ASEAN region, with a total of about 225 million tons of CO2 release, and that's probably an outdated figure. So that's why it's something that we are looking into, and policy making is something that will help this. So ways to reduce that, of course, like I said, replacements, changing, giving new concrete, recycling, aggregates, etc. And a lot of this involves policy making. So when the government comes up with some policies to say, okay, we need to hit down this direction, that sort of helps because, let's say, for example, if we introduce carbon tax, then the industry is then forced to do something. But we don't want to just look at that aspect, okay? We are looking at, finding cleaner ways to do it as well, okay? Now, I mentioned this already. So what are the solutions, okay? These are just general solutions. I'll talk through some of the solutions here and also cover some of the research that we do in these areas. So nanotechnology is something that is common. It gives opportunities where we then enhance the properties of the materials by working at the atomic or molecular level. Because once you can strengthen the molecular structure, then perhaps we can then reduce some of the high carbon emitters in terms of the materials itself by reducing the amount of high strength concrete that is in there. Of course, we are talking about learning from nature, just like how the bone, our bone structure is able to withstand a lot of forces, right? Because it looks at a very high, packing density, and can we then translate this packing density to concrete at the nanoscale? Because if it can be achieved, then obviously there'll be less CO2 emissions into the atmosphere. We also look at carbon nanotubes, but of course the most common solution, the general concrete world, is to look at green chemistry. This is to look at the cement itself and then find out ways that we can enhance that cementitious material and how it's produced, and also at the tail end, which nobody likes to look at, which is the disposal portions of it. Now, lastly, the other solution, of course, is to look at recycling materials. This is also one aspect that sometimes may or may not be, maybe neglected, I would say. Just as a general report, the US itself does produce quite a fair bit of industrial byproducts this after demolition. So there are lots of opportunities where, say, something like concrete debris can be reutilized either in the form of aggregates or other, construction materials, rather than just going into landfills. Okay, so that's some opportunities there. Okay, so I've talked a little bit about this already. I'm going to move on. So geopolymer concrete, I think the last 2 decades or so, this has become more and more popular. In fact, when I first started working on geopolymer concrete, specifically in the area of fire, it was not very well understood. In fact, the guy who coined geopolymers before it was introduced to concrete didn't quite think that this is a suitable material, at least for the construction industry. But of course, we've gone very far, a long way now, and this has been actually proven that it could be done. So what it is just basically a process of taking some, activators, introducing it with some materials that is high in aluminosilicate, okay? And then that process, it emulates sort of the process of cement mixes with water, and then it produces a concrete-like, or rather a cementitious paste-like material called geopolymers. And then, of course, we add the aggregates in there. But of course, the problem here is that there are a lot of chemicals involved. And one of the projects that we shall be introducing in a little bit talks about how we can then address that issue. But there are many opportunities here because it's very good in terms of rapid strength development, superior in fire resistance. In fact, my PhD is all on fire resistance of geopolymer. And it's very suitable for certain applications like, those in areas where you've got a lot of chemical attacks. It's got excellent resistance. And of course, the beauty of this approach is that there is zero, it's cementless. So there's no cement in the mix itself. And we're using a byproduct, which is largely fly ash, pulverized fly ash, or slag, or even red mud to make this happen. Okay, so that's the general geopolymerization process. Okay, if you look at it, comparing it with side by side with what a typical Portland cement will look like, this would be, the aggregates will remain the same. The replacement here is that you have the alkali activated binders, or I guess aluminosilicate, and also some activators, some chemical activators, in placement of the cement and water. Okay, so the precursor has changed a little bit. Of course, the curing process may also change a little bit. Usually, it would involve a little bit of heat that's required, and therefore there is some levels of emissions as well that we need to look into while we work with geopolymers. Okay, so that's, as we mentioned that already. Now, the thing about this is that we've often heard partial replacement of cement in the mixed design, right? And this is very common, and they are formed in terms of blended cements, right? But we're not talking. But the problem with blended cements approach is that cement still has a large contribution, or rather a large embodied energy. As you can see from this particular table here, cement does make up a large amount. And even if you have a small additive, it's not going to do enough to rid of this amount of embodied CO2. But of course, if we are to replace this amount altogether, this is where the beauty comes in, and that's the hope of really tremendously reducing this impact. So what I'm trying to say is that partial replacement, although the cement industry will tell you that it helps, of course, improve some properties, etc., it's not going to make much of an impact if you look at this particular table over here. Okay, so I'm going to skip through this because I think most of us would know some of the trends and applications. It's usually used for patching work, some areas, marine applications where it's got very good chemical resistance or sulfate resistance, therefore making it more suitable for some marine construction. It's got very low thermal conductivity as well, so very good for as an insulating material. Sometimes it's also used as an absorbent to remove metal ions from wastewater. So the applications here are plentiful. You just got to look through and find a way for to utilize it in place of the regular cement. Now, I'm just going to highlight one particular project here that we work together with several universities and also industry partners. This is a large project that is funded by the UK and also Malaysian government, and with collaborators from both ends of the world. On the UK side is led by Professor Marius Soutsos, who's part of the Queen's University Belfast. And this project here attracted a funding of about 6 million British pounds to get both the industry of both continents to work together, and also the universities to work together to try to. And the main goal here is really to see whether we can actually bring it from just a laboratory setting to how it can be scaled up in the large sense. Okay, so that's the main project. Okay, and it's still ongoing, by the way. I'll talk about the project. So this is shortened name. The long name is Low Carbon Footprint Precast Concrete Products for an Energy Efficient Built Environment. I know it's quite a mouthful, so we call it LowCoPreCon for short. And of course, there are altogether about 10 work packages in here to work through this large project of multidisciplinary project. You've got several areas here which I won't go through too much, but it's been a 5-year project right now, and it's still ongoing. But we look at all aspects of it. But I think I want to showcase this project right here is because we are trying to look for ways to bring the development from the laboratory to upscaling and also the commercial scale, because that is always the main barrier of it being utilized. So we've also gone and harvested and produced it in large scale, which I'll show you in a little while in the next couple of slides. All right. But some of the challenges I would say before I even go there is that there are a lot of variability in the source materials because we are working with a industry byproduct. So some of the things is a bit challenging when you get large quantities worth of it to be applied in the industry. It's because there are lack of adequate standards, I would say, to control the material. Now, one of the things that we looked at in this particular project is that we, instead of just looking at or reducing costs per se, I did mention to all of you earlier that the challenge here is the chemicals, right? The chemical activators. If you look at this particular chart over here, the chemical activators, all laboratory projects that's been done to date mainly look at utilizing pure laboratory grade chemicals. These are sodium silicate, the likes of sodium silicate and the likes of sodium hydroxide in tandem with the byproducts here. So the cost is fairly high when you're using lab grade materials, and it's not practical, right? As opposed to Portland cement, you can see here, they don't have any chemicals, that's one. So the cost is definitely mainly coming from the Portland cement. Fly ash is very cheap, as you can tell, but the main bulk is the cost of the pure material, the pure chemicals, right? So one of the things about this project is to try to investigate an alternative and low-cost activator that could then be utilized to make this more feasible. So we looked through several methods of producing silicate solutions using, say, convection heating method, some hydrothermal processes, which is the distillation of, in the UK, there's a lot of solid glass cullets. This is heated with sodium hydroxide solution under pressure. On the Malaysian end, we tried to use the thermochemical process, which is to take solid mixture of sodium hydroxide and glass cullets heated up in an oven, and then you form this sodium hydroxide fusion, and it dissolves and becomes sodium hydroxide. Okay, so this is some of the ways that we try to come up with an alternative low-cost activator. Some of the processes are shown over here. Okay, I will not go into too much details because I don't think I have enough time, but ultimately we have shown that some of the strengths of the concretes that are produced with these alternative binders is actually as good as those laboratory grade ones. Okay, this is utilizing rice husk ash, which is high in silica, and so rice is quite it's quite abundant in this part of the world. So utilizing rice husk is actually good because otherwise it would just be disposed of in landfills. Okay, or sometimes it's being utilized to fuel boilers. There is a high yield of sodium silicate that can come out from this process of producing sodium silicate, right, using rice husk ash. So again, we've done the processes, we've checked it against performances of the various what we call home-brewed silicates, and you can see that the results are quite comparable, and therefore by putting it against the the chart rather, earlier chart that I've shown you, you can see that the costs with this process has decreased rather, because the sodium, the silicate portion of it is tremendously reduced in terms of costing, so making it more comparable to the Portland cement approach. Okay, and this is therefore making it a bit more attractive and usable. Okay, I'm just going to speed up across. He did a lot of tests, optimizing the different parameters. Again, this is more laboratory grade, but we're trying to produce it in large scale. So at the end of that project, we've actually produced a lot of home-brewed silicates in terms of having 4 to 5 cubic meters of solution, and that's 3,000 to 4,000 liters worth of material, because we are to then scale up in the factory side, right, with the industry partners. So that's what we've done. So you can see here factory upscale, both in the UK and Malaysia. These are some of the manufacturing of the blocks, the building blocks. We've got staircases, we've got slabs. We've also got identified, workable mixes, early strength development, also final specimen strengths. And you can see here a picture of some of the stairs that's being built. Okay, some samples over here. So you can see, if I didn't tell this is geopolymer concrete, you probably will not even know. So we've made building blocks, pervious paving blocks, structural elements such as slabs, stairs, beams, etc. You name it, we have it. Okay, and here you can see some panels over here, some foundation things. This particular section over here shows some slabs being constructed, and we actually have laid a foundation, or rather there's some pad footings at the bottom over there, but this slab here actually is supporting this data center. Okay, so we've actually done this precast products, a particular application, and these are purely cementless. Okay, so concrete building blocks, paving blocks, pavement flags, concrete stairs, rain screed facades, different voisoirs. These are the things that we've done in this project. Now, one of the highlights of this project is actually to construct a footbridge, okay, a flexi-arch bridge. We're in the final stages of actually erecting that footbridge. You can see some photos over here with the foundations. The spandrel wall is shown over here. That's already completed. Here you can see a paragrid. So these are actually voisoirs or blocks linked up together with a paragrid. And again, all these are pure geopolymer concrete. It's going to be constructed or rather erected here in Malaysia. Okay, we're in the final stages because all these are precast. Challenges that we have here is obviously you may know that geopolymer sometimes require high elevated temperature curing. Curing it in small laboratory scale stuff is no issue. But if you put it in a large scale setting, it can become a challenge. Like these spandrel walls, it's almost impossible to find an industrial grade oven to do that. So we have to tweak the mix itself to make it room temperature. Fortunately, here in Malaysia, our ambient temperatures are a little bit higher. In the UK, there are some issues with curing because it's generally a lot cooler over there. Okay. Also got some precast modular blocks being constructed. This is just a mock-up. It's going to be completed by March of next year. As in, the panels are already done. It's just going to be erected to see. And this is a modular construction where we can have 3 or 4 story high structures, precast, all in geopolymer form. We can then use that to demonstrate how effective the constructibility is of this material. Okay. We also did long-term life cycle analysis because, like I said, it's a cradle to grave approach because not many people understand what is the life cycle of this particular material. And it was a little challenge in this project to even tweak out some of the consumption of producing it because while the chemicals itself, the home brewed silicates have been found to be cost effective to make, but there's also some heating that's required to produce those chemicals, easy enough to put in a beaker and then mix it up. But if you're talking about large volumes, it was difficult, and we had to then even scale up the process of getting industrial. I would say it has to be some processes in a typical precast yard has to be changed because we're talking about storing chemicals. We're talking about even producing homebrewed silicates within that particular site. So there's a lot of environmental assessments that has to be done, and also safety aspects has to be increased because we're dealing with chemicals in a conventional precast yard. Okay, so I'll stop here for a while. I'm going to run through another project, which very quickly, this is just utilizing some typical admixtures to improve geopolymer, part of the same project as well. The idea here is to use conventional admixtures to improve some of the performances or even the handling of geopolymers. Now, some of the challenges that we have in that particular project is that some of the precast panels actually does set a lot quicker than we expect. So after mixing, there were, of course, talking about large scale, right? We're talking about a panel that is fairly large. And of course, we had some problems with that. Okay, so this is just a small project where we look at different mixed designs to try to improve the composition. We use naphthalene-based plasticizers and also polycarboxylic plasticizers to see whether we can. And these are just conventional plasticizers that we normally put into cement and see whether we can tweak it and utilize it with a pure geopolymer-based application. Okay. So I'm just going to skip ahead, jump to the conclusions. I guess they'll help. Some areas of work. This all is to be shared anyways. You can have a look at it more clearly later on. But needless to say, there was some success in actually having some effectiveness in utilizing some of these material. Okay, so that is that particular research project. Now, another interesting thing that I want to talk about very quickly is also we've utilized graphene oxide and halloysites, try to improve some prior properties of geopolymer concrete. Okay, and what we've done here, obviously, geopolymer itself is quite good in the areas of fire, but I think we want to take it out another further. So we're utilizing different nanofibers or carbon nanotubes or even nanosilica into the cementitious matrix to see whether we can actually improve the performance. We're specifically focused in this particular project on the graphene oxide and also hybrid filler, or in other words, halosites over here. Okay, so just click on the next slide. So showing you some of the things that we've done. There is a particular video that will show you how the process is done. I think that will probably summarize everything, but we've taken some steps to identify the nanoparticles to be utilized, tweak the methodology to incorporate the nanoparticles into the matrix, And then, of course, the latter stages will be looking at investigating its performances in the area of post elevated temperature exposure. Okay, and then we look at some of the microstructure to see what has happened. Okay, we've checked it for 3, 7, 28 days strength. Just to give you an idea, this is just a preliminary work. It's a 1-year project, so whatever we have is just preliminary. Okay. So we look at constraints, materials that we have. One thing we have to quickly mention here is that it's some of these materials that we're utilizing is not cheap. So that's why it's one of the main constraints here. So we got to be very careful with the amount that we utilize. Okay. Let me just see whether I can play this video. I think that would help. Okay, this shows you the entire process. I think it will only be 2 minutes. Let me just play it. So you can see here the process of getting the alkaline solution prepared, and then they introduce the graphene oxide and the halosite into the mixture. We've done several processes of sonication of the material to try and improve and see whether that actually helps. This is a particular grad student that's preparing the molds for casting. This process is just preparing the materials and the raw ingredients right here, your typical geopolymer mix design. Let's see here, it's being mixed, and then of course here's where we add your chemicals and also the nanomaterials in there. Okay. As you can see on the surface, it's not much different. Several tests has been done, seeing how it behaves in terms of the workability. Then after these tests have been conducted, we've also gone ahead to then move on to casting the samples. There is some curing that is required for these samples. You can see that it's still being prepared, and then after that, I think there'll be it's vibrated. So combination of tamping and vibrating table for compaction. And you can see here the student is putting it into a curing tank. I think we've gone for a 70 degrees Celsius for a period of 24 hours, if I'm not mistaken. Okay. Of course, these are some of the tests that's been done before temperature application. And then here you have the samples that are being exposed to temperature and then tested again. So we look at residual strengths before and after elevated temperature exposure. Okay. I think I'm just going to stop here. So yeah, we have seen that the materials does increase in performances after we've introduced the graphene oxide. So there's a lot of optimization here. But some of the challenges that we have is that once we have too much of these particular, say, graphene oxide, there is a problem with dispersion of the material, and some of the overlapping of the material can actually lead to some decrease in strength. So we've seen that problem. As I mentioned to you before, we've looked at the process of sonicating versus no sonication. So just to see whether some of these additional treatment does do the performances. Okay. So comparing it with the different ages, you can see that there is some increase in strength from 7 to 28 days, even after the elevated temperature performances. So as I mentioned to you, this is the sonicated version versus untreated GO, graphene oxide. And we do see that for the lower graphene oxide dosages, the sonication does have a positive effect. For higher dosages, somehow it doesn't really do much to it. So it would be better to not having to have the extra process of sonication. Okay. So as mentioned, if the dosage is small, which is what we want, sonication is actually a good approach. Okay. I'm just going to. We've also introduced halosites over here, a combination of the two. Although this is just very preliminary, there is some beneficial influences in terms of the elevated temperature performances. We hope to do a bit more in this particular field and area. Look at the microstructural behavior as well, just to see how the different things react to it. But as I mentioned to you earlier, some of the conclusions that we have is that it's actually a very costly material. And we are looking at further enhancing this. By the way, this is just an FYP project. So we didn't expect too much of it. We probably take it a bit further because we've seen some preliminary positive results from this particular work. Okay, some major conclusions over here. Like I said, it has shown improvements, and we will probably take this further in terms of optimization. Okay. Now, I'm just going to quickly, I'm sort of ending here in the concrete area, but I want to highlight another project that's interesting over here. Although it's not in the area of concrete, I think some of the principles may be translated into some of the concrete projects that we're working on. I've got the privilege to also supervise another student who's looking at encapsulation of rejuvenators of asphaltic pavement material. Okay, so this is the focus here is on the encapsulation process. Just some introduction for those of you who are not familiar with the asphaltic pavement area. Asphaltic binder over time does crack over time because of the changes of temperature. So one of the ways to do this is actually to introduce some healing agents in the form of oils, and that actually, once it's introduced at the correct timing, it does enable material to self-heal. Okay, but the problem is, how do we then embed it into the matrix? And some of the ways that we've done this is actually to find ways to encapsulate these self-healing materials, and then when it's required, it will then crack open and then release the agents to the matrix. Okay, so this is what we deem as rejuvenators. So of course, it's not just one-off use thing. We are looking at multiple utilizations of it. So I'm just going to skip ahead from this literature review portion of it. This talks about the different encapsulating materials that can be used, and also the different rejuvenators, which I will skip ahead. Things like sunflower oil, calcium alginate is also used as an encapsulating material. But the theory here is to have a multi-bead layer. This is having multiple layers of encapsulation to then have multiple releases of rejuvenators over time. That's the process. Now, how are we going to do this is probably the main novelty of this particular research project. And as I mentioned to you, it could also be translated into other applications. Okay, let's skip ahead of this thing. I think it's too detailed. Okay, just going to move on to here. So things that we've done is that we use different rejuvenators, sunflower oil, palm cooking oil. Now, palm is a big thing here in Malaysia, so therefore there's some motivation to use palm there. We use base oil as well. The encapsulating material, or the pill per se, is called the calcium alginate material. And how do we then produce that is what we're focusing on. Okay, some of the asphaltic material mix here that's also discussed. The process of encapsulation, literally, you can see it being dripped in, and in that process of dripping in, it creates a bead, and then that bead encapsulates that particular material that's supposed to be in there. Now, creating the multi-layers is probably what we are working on, all right? I'm just going to skip ahead over here. So you can see there we've done different things like optimizing bead size, what type of shape that we're getting. And here you can see we've also done Fourier transform infrared tests, whether or not the material is actually encapsulated well. And you can see before and after encapsulation, the peaks actually matches over here. So some of the rejuvenators do not contain the peaks between these spectrum, indicating that's actually successful in terms of the encapsulation stages. Okay, I meant to click on this so you can see this particular thing here. Okay, so that's good. What else do we have here? I think I'm going to go into the spectra does show noticeable decrease in two of the peaks, namely in this region over here. And these peaks actually depict the OH and group that overlaps with the CH group, according to this particular author, due to the additional layers covering any exposed pores. Now, additional layers covering any of these pores are actually detected over here. Okay. Now, looking at this, we have actually taken some samples. We've actually induced a crack. Okay, and then let it self-heal and come back and measure, how well it's actually healed. And you can see that the gap actually has healed again. Okay, and then of course we've gone and applied some tests to see whether it was firstly the crack, whether it's continued to propagate. No, it didn't propagate. And we've seen some healing whereby after cracking, it's actually healed. So that's a good thing. Okay. So we've also gone and measured the healing efficiencies over here. And you can see that go ahead and measure some healing efficiencies over here. Now, of course, as I mentioned to you, this main thing here is not so much on the healing processes and efficacy, but more on the methods that we've adopted to have a multi-core encapsulation process, which we then hope to translate to some other applications, maybe in concrete applications, etc. Okay, so I'm just going to end here, and I'm just lastly going to say here that sometimes when we focus on improving any materials, whether it be concrete or anything, we look at just the material, but the barrier is actually not on the material itself. Sometimes it is more than that. We need to come to a holistic approach, and I really believe that education and research has to go hand in hand. So there needs to be some reform, I would say, in the area of education research to ensure that we're also building a generation of people that are willing to change the perception of industry. This simple illustration here is always is very common. I think most of us would know this life cycle, but we often just look at micro scales and not the macro scale. I think we need to then shift to more macro, even whatever research that we do. Now, building codes is another institutional barrier that's discouraging the use of new novel materials. I would say in general, a lot of perhaps the design codes are out of date because it doesn't allow the use, or it specifies the use of particular materials and mixed proportions for a job rather than specifying a particular standard of performance. So I think that will slowly have to be looked into in order for it to become a bit more forward thinking in this area of realization of green materials or even green concrete. Okay. Yeah, I think green materials as a whole, whether in concrete or not, is really more the greening of the mind rather than, legislation aside, it's more greening of the mind, and it's really a responsible of all to look into, because like I said earlier, it has to be a reform from within. Now I'm going to end here. I think I've gone over time. If there are any questions, do feel free to reach out to me. My email address is here. My research partner in the UK is also right here if you need to reach out to any one of us. Okay. Thank you.